Hi everybody, my name's Cameron and today we're going to be looking at matter and radioactivity. We're going to be looking at radiation, half-life, nuclear physics and just the different states of matter. So we know that the law of conservation of matter states that matter cannot be created or destroyed. It just changes forms. Okay, the three main forms we look at are solid, liquid and gas. Okay, you do get plasma. That's something we can go over in another lesson. But we're going to be focusing on solid, liquid, and gas. Okay, now what exactly causes matter to change phases? Well, it is going to be the weakening or breaking of intermolecular bonds, bonds between molecules of a certain substance. Okay, once those bonds are broken, it's still going to remain that substance. It's just going to be in a different form of matter. Okay, so if we look at this graph over here, as you can see, when the graph is sloped, okay, that is the matter gaining energy as the temperature increases. Okay, when it plateaus, that is when it has gained enough energy that the energy is then transferred into the molecules. And that's when bonds start to be weakened and break. Okay, so something like water. Okay, water has a melting point of 0 degrees Celsius. But water at minus 10 degrees is going to have more energy than minus 20, even if it's still a solid. Same thing with the water's boiling point. Okay, water will be changing into a gas at 100 degrees, but at 90 degrees, it's still going to be incredibly hot, but it won't be a gas until it hits that boiling point, you see. So when it plateaus, that is the transitioning into the next state of matter, and then as the next state, it will continue to gain energy as you increase its temperature. So now we're going to be looking at gases and pressure. Okay, so gases exert a force on their container. Okay, how does this happen? Well, gas, as we know it, has a lot of energy. Okay, these atoms are moving and vibrating a lot, and a lot more than just solids and liquids. Okay, and it's that exertion on the walls in all directions of the container that we call pressure. Okay, and as the temperature increases, so the pressure. As the atoms are going to be moving faster and they're going to be moving with more force. Okay, so as temperature increases, so does pressure. If temperature, however, is constant and the volume of the container is increased, so the size, let's say, of the container increases, that means our pressure is going to decrease, okay, because there is more space for the atoms to move around. If, however, our volume decreases, there's a smaller space for the atoms to move around. They're going to be hitting the side of the container more, and therefore the pressure is going to increase. It's this relationship of decrease in volume and increase in pressure and vice versa that we know as Boyle's law. Now, we just talked about the conservation of matter, but we also have the law of conservation of energy. Now, energy cannot be made or destroyed. It can only be transferred from one form to another. And it's that transferring of energy that we call radiation. Okay, so we measure radiation using something called a Geiger counter. Okay, it makes like a clicking noise when it gets closer to something that's radioactive. You might have seen in the movies. And there are three specific types of radiation that we're going to be looking at. We're going to be looking at non-ionizing and ionizing radiation. So ionizing radiation is going to be like our alpha and our beta radiation types. Okay, alpha being the one that is the most ionizing, it is the least penetrative, okay, whereas gamma is going to be our waves, so you get gamma waves, alpha and beta particles. Okay, and we're going to get to that soon, why that's called that, okay. So alpha particles are the most ionizing, least penetrative. Beta, kind of in the middle. Gamma rays are least ionizing, and they are very penetrative. Okay, they go through most forms of matter. So ionizing radiation is when a nucleus of an atom is going to lose energy and it's going to be split up. Okay, this is what we call radioactive decay. So a lot of radioactive materials, ones that occur naturally and ones that are man-made, are very unstable. Okay, so their atoms are constantly splitting up. Okay, when they split up, they're going to release this radiation, either alpha, beta, or gamma. Okay, alpha particles, okay, are going to consist of 2 protons and 2 neutrons. Your beta particles are going to consist of an electron that is shooting off, and your gamma waves, they're just gamma waves, they're just energy. Okay. So we talked about radioactive decay being the breakdown of these unstable atoms. Okay, so if it's alpha radiation that is released, it's going to be 2 protons, 2 neutrons. That means the atomic number is going to decrease by 2. It becomes a new element. Okay, and the atomic mass is going to decrease by 4. Okay, the charge is reduced because there are now less protons, representing using the notations such as the ones on the right here. So you see we have a helium, and this element has changed now. Okay, it went from Ra to Rn. I think it's rubidium. Okay, now beta radiation is when the neutron changes to a proton and an electron. Okay, is released. The created electron is then released. The atomic number increases by 1. The atomic mass is unchanged, and the charge is increased. Okay, it's represented by this notation here. So as we see, an electron is released. Our atomic number increases by 1, but our atomic mass stays the same because that neutron became a proton. Okay, and then gamma radiation is electromagnetic waves, so there's no change to the atom's atomic number, mass, or charge. It's just a release of energy. So we know that this radiation can be referred to as ionizing radiation. So it basically leads to a knock-on effect. Okay, as one atom is broken apart and that radiation is going to be let out, it can hit into other molecules, okay, and cause damage to those molecules, thus irradiating, making that object radioactive. You see, so a lot of the times with these power plants or nuclear power plants, okay, people can have radioactive clothes, let's say, clothes that are contaminated with radiation. You see, radioactive energy. That radiation can lead to burns, cancers, a breakdown of your molecules. Okay, it can also be a specific level of penetrating. Okay, we said alpha has a low penetrating level. It can be stopped by something like plastic, even if it is very ionizing. Something like beta particles are less ionizing, okay, but more penetrating. So they would be able to go through something like plastic. A great question that they love to ask is that of the smoke detectors. Smoke detectors, I think, do or used to have a radioactive material in them that emitted alpha particles, blocked by some plastic, so it was safe for everyone to be around it. But it's important to know that it was okay only because it released alpha particles and not beta particles. Okay, so ionizing radiation can also be used in the medical industry for something like x-rays, in manufacturing of something like smoke detectors and certain treatments. So, we said earlier as well that this decay rate, okay, the amount of time it takes for an atom, an unstable radioactive atom to break apart, it's a random process. Okay, we have no idea how long it'll take for one atom to. But what we can do is we can measure something called the count rate, which will tell us the half-life. Okay, so the count rate is basically how many of these atoms in a sample are going to be radioactive and how many have turned into the stable other element. Okay, and the half-life is going to be the amount of time it takes for that count rate to fall by a half. For half of the radioactive atoms to become non-radioactive or to change into the other type, would be called the half-life. That will take a certain amount of time that we can measure. Okay, and then the amount of time that it takes for that half to half is the next half-life. You see, and depending on how radioactive something is, its half-life will either be shorter or longer. Okay, some things can have a half-life of thousands and thousands and thousands of years. Others have a half-life of only a couple hundred years. Okay, and that's when we use it to date various objects and fossils that we find. We can use different substances, okay, such as either carbon 14 or uranium dating, okay, depending on how old your sample is. So as we mentioned earlier, radiation can also be used in medicine, okay, not only as x-rays, but as radioactive traces. Okay, this is when they inject a person with something like iodine, okay, and it emits radiation detected to analyze kidney function. Okay, so sometimes if they want to check out your lymph nodes, let's say your lymphatic system, what they'll do is they'll inject you with a radioactive liquid or something like that. It will be absorbed by your organs and sent to the different lymph nodes. Now, let's say that all of it shines up on your left lymph node, okay, and not your right one. Then they know that there could be something wrong with your right. You see, it works something like that. Another one would be radioactive cancer treatment, okay, to kill cancer cells, as well as radioactive implants. Okay, this is when they take a seed, they put it into the tumor, and it'll kill the cells around it. Okay, thus killing the cancer. Now, the half-life is going to be long enough to be effective, so it's not going to decay too quickly that it's not going to work, okay, but not too long that it's going to make the person radioactive and possibly give them cancer in other ways, okay. So again, we would sometimes use gamma radiation as it's going to penetrate the body with minimal damage to the healthy tissue, because if we were to use alpha or beta particles, they are highly ionizing. So we don't want it to damage your cells, unless that's what we want it to do. Okay, so when it comes to nuclear reactions, we can also create energy from this, or harness its energy to generate electricity. Okay, and what we're currently doing is nuclear fission. Okay, so we do that in those nuclear power plants. This is the splitting of those atoms. That energy is then going to be used to heat up water, which is going to turn a turbine. Okay, now what we are currently trying to do is nuclear fusion. Fusion is when we're going to be joining nuclei, the atoms' nuclei together. This is going to create a release of energy, and it's going to be a lot cleaner than current nuclear energy. Okay, right now fusion is only happening in the sun, but we're trying to do it here on Earth as well. Okay, so let's look at nuclear fission in a bit more detail. Okay, so it usually is going to involve either uranium or plutonium as the fuel, okay, the unstable atoms or unstable elements. Neutrons are going to interact with these unstable uranium nuclei, and that's going to cause them to decay. It's going to cause them to break apart. We know that when they break apart, they're going to be releasing energy, okay, and they're going to break apart into what we call these daughter nuclei, and it's going to release more neutrons, which is going to cause a chain reaction. So it's going to cause other uranium particles or plutonium particles to also decay. Okay, so when we look at a nuclear reactor, the components are the fuel rods. The fuel rods are going to be your uranium or your plutonium. They provide the energy, the atoms that are going to be converting and releasing energy. Okay, we then have a moderator. This is high pressure water that slows down the neutrons, okay, making it a bit more controlled so we can capture their energy in the coolant, which is going to transfer that heat to produce steam and the electrical generation. Now, we also need a way to cut off this radioactive energy as quickly as possible if something were to go wrong, or if we just want to turn it off for a while, okay? And what we're going to use there is a control rod. The control rods are going to be absorbing extra neutrons to control the reaction. Okay, I believe they use carbon for this, or lead. I think it might have been lead. Yeah. So as soon as those control rods are put in, the reaction gets cut off, and it's going to house those nuclear fuel rods. Okay. Now the advantage is it provides large amounts of energy and low greenhouse gas emissions. So it's only going to be producing steam. Okay, which is what clouds are made out of. But the disadvantage is it's very expensive, long decompositioning process, as well as radioactive waste disposal is required. If that radioactive waste is not disposed of properly, it can leak out into the environment and cause collapse, okay, as it kills all life, mutates life, really not good, okay. But it might be a better alternative than carbon emissions from our coal factories, okay. Now, when it comes to nuclear fusion, this is what we're trying to get right at the moment with these massive machines, okay? It usually only occurs in stars, and what it's going to be doing is combining these smaller nuclei into a heavier nuclei that's also releasing energy, okay? But it requires extremely high temperatures and pressure, not something we're able to do just yet, but I think it was Japan that has recently had some breakthroughs in nuclear fusion. And the potential advantages is abundant energy as well as abundant hydrogen, minimal waste, and yeah, large energy output. Okay, so hopefully in our lifetime we can experience nuclear fusion. It's basically going to be almost free energy for everyone, everywhere. Okay. So, my name's Cameron, and I'll see you in the next lesson.